Recall that the ellipse is one of the three main types of non-degenerate conic sections, so we would like to study it further in this video lecture. In our last video, we learned about the parabola. In this video, we'll learn about the ellipse, and in the next video, we'll learn about the hyperbola. If you recall from our last lecture, when you slice a double-napped cone with a plane, then depending on the angle of the slice, you get one of these three main types of non-degenerate conic sections, and of course the three degenerate ones which we've talked about before. But if the angle of the cut is somewhere between the angle of the vertex for the double napped cone, called the vertex angle, and 90 degrees, then we end up with an ellipse. If the angle is exactly the same as the vertex angle, the angle of the slicing, then we get the parabola. And if the angle is less than the vertex angle, but of course greater than 0, we end up with a proper hyperbola. Today, of course, we're interested in the ellipse. Formally speaking, an ellipse is the set of all points in a plane, the sum of whose distances from two fixed points is constant. The two fixed points are depicted here. They're called the focuses or the foci, the singular, of course, being the focus. This creates two axes for the ellipse. They're both going to be axes of symmetry for the ellipse. One, the longer one, as long as we're dealing with a non-circular ellipse, is called the major axis, and the shorter one is called the minor axis. And the points of intersection of the ellipse with those axes are called the vertices if it's the major axis we're intercepting, and co-vertices if it's the minor axis that we're intercepting. Notice that the foci of the ellipse are always going to be on the major axes of the ellipse, and we associate the letter A also with the vertex that falls on the major axes of the ellipse. Next, we're going to explore some interesting relationships between the three numbers we've introduced, basically A, B, and C. Now, basically, all you're doing is you're picking a couple of points in the plane and fixing them, and then you're fixing a certain distance, which is the sum of these two pieces that you see here, the distance between that point and either focus. And when you add those two distances, you should get a fixed number. That number is also something you decide to fix. So then what's created is an elliptical shape that you can see here. We're going to look at an interactive that really demonstrates this well and bring it home for us. So let's go ahead and take a look at that. Now, in the olden days, we actually did this with hand. So nowadays we can kind of demonstrate it digitally like this, as is done by Audrey McLaren from using the great software called GeoGebra. But I strongly recommend that you try this for yourself. Basically, you take two thumbtacks, put them in something like a cardboard of sort, then take a piece of string of a certain length, whatever length you like, and then you draw it until it's nicely tight here, and then you just go ahead and just start keeping it as tight as possible. You go ahead and start moving it like this, okay? And as you do, you're going to basically draw the ellipse. Now, of course, the way this software works, you're not going to see it completely plotted out unless you keep going over it many times. But when you're doing it with an actual pencil, it's just going to be a nice solid elliptical shape. But this demonstration does really well as to what's happening here. Notice that this length of the string here is exactly what's fixed. Here we've fixed it at 10. So notice these two distances can change as long as their sum remains constant. You see, keep your eyes on this interactive here, what's going on. Notice the length of each of those pieces changes, but the total distance between the point and the two focuses remains constant. We're going to look at another interactive because we want to look at two basically important points. One right there, when the pencil falls on the vertex, one of the two vertices, and then also when it falls on one of the co-vertices here. And that's what's going to enable us to find the relationship between the letters A, B, and C that we talked about. So let's go ahead and go to that interactive now. Here we have another nice interactive by Interactive Mathematics. Here the length of our string is 16, and notice how as the point moves around, once again, that distance remains, that sum remains fixed even though the two distances change, right? Now we're going to be interested in this particular point right here, which is where the vertex lies, right? And also where this co-vertex lies. We're going to look at that more closely and find out some interesting things about an ellipse. So let's go ahead and do that. So in this ellipse that we have here, the center is at the origin, C0, 0, and the foci are at FC0 and F prime of negative C0, right? And the vertices are, of course, are at A0 and negative A0. We know that because the vertex on the right here, and I could have done this from the left either, it's just a little bit easier to talk about it on this side. Notice that the distance between this vertex and the first focus, F, and the distance between the vertex and the other focus, F prime, should add up to that same constant length of the string, right? Now, analyzing this particular point and its distance from the two foci can easily tell us what the length of the string should be, because notice that the distance from V to F is going to be this distance, which is A, as you know, from the center to the vertex. Take away this distance, which is the distance from the center to the focus. So it's going to be A minus C, right? Now, let's see what the distance between the V and F prime is going to be. Well, notice from here to here, that's A, right? So, and we also know that this distance here is going to be C. So the distance from the vertex V to F prime is just going to be A plus C, right? So if I want to know the length of the string, all I have to do is I have to take that distance and add it to that longer distance. So I get A minus C from here and A plus C from here, and I add them, and of course notice the C's cancel out, so I end up with 2A. So that's how I know the length of the string must be 2A. Now, if you notice when I place the point of interest at the top co-vertex, then I know that this length here is going to be B, right? And this length here, which is basically the distance between the center and that top vertex, right? I know this distance here is C, and we just talked about the fact that this length is 2A, so because this length and this length should be the same by definition, because remember, it's a point on the ellipse and the distance from the two focuses should be the same, and in the sense that it should add up to what? 2a, but then when you divide it by 2, you get what? You get a for each of them. Now, why would that be? Now, why do these two have to be the same? That's a good question, which actually goes back to geometry, because notice that these two triangles are congruent because of the SAS property. You have two sides and the angle between them in this triangle being the same as two sides and the angle between them in this triangle. So by the SAS property, these two triangles are congruent. Therefore, these two, which are corresponding sides, should be congruent. So that's how we know that the 2a should get split into 2 to give us a for each of these two sides here, two segments here. So now we have B, C, and A being parts of the three sides of a right triangle, with B and C being the lengths of the legs, A being the length of the hypotenuse. So we end up with b squared plus c squared equals a squared. Now, we know that from the Pythagorean theorem, but it's nice to verify it from the definition of an ellipse as well. We know that the distance between v bar, which is what we're naming this top co-vertex, to this focus, plus the distance from v bar to the other focus f prime, should be 2a. Now, we're going to use the distance formula for this distance. So it's going to be the square root of quantity 0 minus c squared, right? Plus quantity b minus 0 squared. Didn't want that. And then plus this distance, which according to the distance formula will be the square root of quantity 0 minus negative c, which turns into 0 plus c squared, and then plus b minus 0 squared, and all that should equal to 2a. Now, when we clean this up, notice that's just going to be c squared plus b squared, and that's also going to be c squared plus b squared. So we basically have 2 times the square root of c squared plus b squared equals 2a. So if we divide both sides by 2, we get the square root of c squared plus b squared equals a. Go ahead and square both sides to get c squared plus b squared equals a squared, which is the result we had discussed using the Pythagorean theorem, right? And notice that if I basically solve for b squared, I end up with a squared minus c squared, right? So basically, if we keep b squared on this side, we get a squared minus c squared. To get the a squared minus c squared on that side is no problem. We can do that by the symmetric property, which says if a equals b, that implies b equals a. So we just wrote this equation in the other order. All right, and that's the result we've established between a, b, and c for an ellipse. Let's go ahead and see what we can figure out next. If we now, instead of looking at this special point, which is the vertex, look at any general point on the ellipse, which we'll refer to as p of xy, then we will end up with a really nice equation for the ellipse that we can use from that point forward. So now we know that for any point p of xy on the ellipse, the distance by definition from one focus added to the distance to the other focus should be the length of the string. And we know that if the vertex on the major axis is at a0, then the length of the string is going to be 2a, right? So we can say that this distance added to this distance is equal to 2a. Notice that the formulas we're going to need for our discussion here are just these two or three formulas. The distance between 2 points in a plane, which we've already learned about, the square of a sum formula, and the square of a difference formula. So we'll be using those three formulas in our discussion. Now, if you are comfortable with algebra, I would recommend that you stop the video and carry from here on your own. See if you can get to this point that we've gotten down here. And then you can come and check to see if our work agrees. Basically, we're going to be simplifying by getting rid of the radicals. So a lot like when we solved radical equations that contained two radical expressions, we're going to handle it in a very much similar way. So basically, what we'll do is we'll go ahead and keep one radical on the left side and move one to the other side. So once we've done that, as we did with the equations containing two radical expressions, we'll go ahead and square both sides. And notice on this side, the square root will just go away because we just have one square root expression. So we end up with the radicand, which is quantity x minus c squared plus y squared. On the other side, we're going to be applying this formula, this second formula of the squaring of binomial variety for the square of a difference. So we get the first squared plus 2fl plus l squared. So notice we get the first squared is going to be 4a squared minus 2 times 2a times this radical expression. So we get minus 4a times radical quantity x plus c squared plus y squared plus this second expression squared, which is just a radical expression. Again, when we square it, we just get the radicand, right? So quantity x plus c squared plus y squared. Now we go ahead and expand that by just working it out, and we end up using that formula again, right? So we end up with x squared minus 2xc plus c squared plus y squared equals 4a squared plus, we just basically simplify by expanding that as well. That's going to be x squared plus 2xc plus c squared. We're using this formula now. And then there's a plus y squared, and then minus 4a square root of quantity x plus c squared plus y squared. Now we'll move this expression to the left side, and we look at a bunch of cancellations, right? The x squares should cancel. They're the same on both sides. The y squares cancel out, right? And so do the c squares. So on the right side, we have 4a squared plus 2xc. When we remove this negative 2xc to the other side, we end up with plus 4xc after combining those two like terms. So now we have 4a times square root of quantity x plus c squared plus y squared equals 4a squared plus 4xc. We notice the common factor of 4 in all terms, so we can divide it off from both sides by dividing both sides by 4. So we end up with this expression. Now we're ready to go ahead and square both sides again to completely get rid of the radical. So we end up with a squared, and when you square the radical, you're just going to get the radicand. And on this side, we're going to apply this formula, the square of a sum formula. So we get the first one squared plus 2 times the first times the second plus the second one squared, which is going to be x squared c squared. So now we're just going to expand that. So we get a squared times, by applying this rule again, x squared plus 2xc plus c squared plus y squared. And on the other side, we're not doing anything in this step. Moving on, we're just going to distribute the a squared. So we end up with this expression equals that expression. So now we have a squared x squared plus a squared c squared plus a squared y squared. We notice these two terms are going to cancel out, the 2a squared xc, because we have the exact same term on both sides. So on the other side, we just have a to the 4 plus x squared c squared. Now if we go ahead and move that x squared c squared to this side, and also move this a squared c squared to the other side, you'll see that then we'll have a common factor of x squared, which we can factor out to leave us a squared minus c squared. And on the other side, we can factor out an a squared to leave us a squared minus c squared as well. Now, the goal is to get a 1 on this side, so we go ahead and divide both sides by this expression, a squared times a squared minus c squared. So we end up with x squared over a squared plus y squared over a squared minus c squared, because the a squares will cancel out, right? Equals 1. But if you recall from our previous screen, let me remind you, notice a squared minus c squared we discovered is equal to b squared, right? So if we replace the a squared minus c squared by b squared, we end up with x squared over a squared plus y squared over b squared equals 1. And that nice simple formula at the bottom there, after all that hard work, is the equation of an ellipse, which is centered at the origin with a horizontal major axis and vertices at a0 and negative a0 and co-vertices at 0b and 0 negative b. So this is what we would consider to be tedious but not difficult, because remember, all that's involved is these three simple facts from before that we know. But it's still a significant algebraic feat to be able to get it done on your own, so make sure you can handle that before moving on if you really want to improve yourself. All right, to summarize, we have established that if we have x squared over a squared plus y squared over b squared equals 1, then it's an equation for an ellipse that's centered at 0, 0 with vertices at a0 and negative a0 and foci at c0 and negative c0 and minor axis endpoints at 0b and 0 minus b. So the endpoints of the major axes are basically called vertices, and the endpoints of the minor axes are called co-vertices. Some textbooks use that terminology and some don't, but it doesn't really matter as long as you understand what you're doing. Now, we can do a completely analogous argument and establish the fact that x squared over b squared plus y squared over a squared equals 1 is an equation for a vertical ellipse centered at 0, 0 with foci at 0, c and 0, negative c. In other words, foci on the vertical axis and minor axis endpoints at b0 and negative b0. Notice that we're sticking to the convention that we're going to use the letter A and associate it with the major axes. So notice the equations are very simple, but the similar and simple actually, but the a squared and b squared locations are switched. Basically, the a squared is always going to go under the variables, the square of the variable, which is going to be the major axes. Okay. All right, so you may wonder what happens if a equals b. Well, recall that the center radius form of the equation of a circle centered at 0, 0 and radius r is given by this formula right here. So if we simplify, we just get x squared plus y squared equals r squared. The formula, of course, the main formula we used was the generalized center radius form, which for a translated circle, not necessarily at with center at 0, 0. So it's usually a quantity x minus h squared plus y minus k squared equals r squared. But in this case, both h and k are 0, right? So we end up with x squared plus y squared equals r squared. Notice what happens if we divide both sides by r squared. We get x squared over r squared plus y squared over r squared equals 1, which is basically the equation of an ellipse that we've studied, right? So a circle centered at 0, 0 with radius 1 is just an ellipse centered at 0, 0 with a equals r equals b. Now, you know that c squared equals a squared minus b squared, so we're going to get a value of 0 for c squared, which means c itself is 0. So both of the foci are basically going to collapse into the center, and the ellipse is going to get transformed into a what? perfect circle. That's what happens if A equals B in the equation we just learned for the ellipse. X squared plus A squared plus Y squared over B squared equals 1. Okay, so let's go ahead and apply some of what we've learned to go ahead and graph some ellipses. Now I've put the end product here because you know how artistically challenged I am, but we are going to go through all the steps of finding out how to get it. And of course, a lot of the information we need isn't given here in this image anyway. So the first thing we want to notice in order to graph this ellipse is the fact that the number under x squared is the larger square, so therefore this is going to be a horizontal ellipse. We know that. So this 100 is going to be what we associate with a squared, right? Remember we use the letter a for the major axes. So right, so and we know that b squared is 64. So applying the square root property to both of these equations, we get a equals plus or minus 10, b equals plus or minus 8. So if I were to graph this by hand, I would just put a dot at positive 10 and negative 10. Those are going to be the vertices, right? And then I would put dots also at 0, 8 and 0, negative 8. Then I would just go ahead and connect those, in an elliptical manner, of course. So graphing an ellipse by hand is not very difficult. Again, I try to stay away from that, but you could do it. It's really simple. All right, so as far as the domain and range, notice that the x values involved here are between negative 10 and 10. So the domain is the interval from negative 10 to 10, and it's a closed interval. Both negative 10 and 10 are acceptable inputs for this equation here. So therefore we use brackets, and the range, notice, runs from the set of the y values associated with this graph run from negative 8 to 8. Again, we use brackets because those two endpoints are fine as well. All right, so the center for this, of course, is at 0, 0. The vertices are at 10, 0 and negative 10, 0. What we can do is we can use this compact notation and just put like that, plus or minus 10, 0, and that's actually 2 points, as you know. One of them is 10, 0, the other one is negative 10, 0. The endpoints of the minor axes, which we have been calling covertices, right? So the covertices are at 0, plus or minus 8. Now the foci we need to find, right? Because we have A and we have B, so we can find C because we know that, remember, this is B, this is A. We know that A squared plus B squared, right? This is actually, A, and this is B, but the C is going to be somewhere here. So if you recall, we had our equation was A squared minus C squared equals B squared, right? So if I solve that for C squared, I get A squared minus B squared equals C squared. So 100 minus 64 equals C squared. So C squared equals 36. So C is going to be plus or minus 6, right? So the foci are going to be at, remember, they're always going to be on the major axis, so they're going to be at 6, 0 and negative 6, 0. If we want to write it in compact notation, we'll just put at positive, negative 6, 0, like so. Okay, so that's how you would graph an ellipse and find all those parts. So if you ever forget this relationship, no need to panic. You can just recreate it. We know that if we have a general ellipse, we know that this is B right here, right? We know that focus is going to be somewhere here on the major axis, right? And we also know that this distance here, right, is A, and we know that this piece here is C, right? The distance from the center to either focus. So then you can just quickly see that you either have B squared plus C squared equals A squared, or you have different versions of it, right? You have B squared equals A squared minus C squared, or you have C squared equals A squared minus B squared, etc., right? So no need to panic if you can't recall it. You can just recreate it, right, very quickly. All right, so there we go. Make sure you can handle that, and we'll proceed. All right, so now we're going to do the same for this equation. Doesn't look like an ellipse at first sight, but if you work on it a little bit, you can see where that could happen. So what we're going to do is we're going to go ahead and put it in the standard form that we have found, the form x squared over a squared plus y squared over b squared equals 1, or the other one, x squared over b squared plus y squared over a squared equals 1. Both of them are called standard forms of an ellipse. This is closer to a form which we call the general form, not exactly like this. Every term would not need to be on the left side with 0 on the right side, and we should always be able to go from the general form to standard form, and that's what we're going to do here. So we're going to go ahead and move the x squared and y squared term to one side. And since we know that we are going to want a 1 on this side, we're going to go ahead and divide both sides by 560. So we end up with this, right? Now we'll go ahead and see if we can simplify as much as possible. And for that end, you can either do it in your head if you're comfortable with the numbers, or you can just use a calculator. All right, so let's see if 20 goes into 560. So we divide 560 by 20. So we get 28. So we can cross cancel, and we get x squared over 28. And now we'll go ahead and see if 7 goes into 560. I believe it does so 80 times, but let's just be sure. Yeah, so we get plus y squared over 80 equals 1. So because of the fact that the larger number is under the y squared, we know this is going to end up being a vertical ellipse as depicted here. So, but you can see that you still are going to have to get exact values for the co-vertices here and the vertices there, etc. So we still need to do some algebra. So we know that our a squared is going to be 80, and b squared is going to be 28. So this implies that a is going to be plus or minus square root of 80, and b is going to be plus or minus square root of 28. Now these are both pretty nice numbers that are easy to simplify from under a radical, because that's like plus or minus square root of 16 times square root of 5, right? And that's going to be plus or minus square. So we basically look for the largest perfect square factor of 80. If you factor 80, you get 240, 220, 210, 2, 5, and 5, 1. So on the left here is the prime factorization of 80. And you can see all of that is a perfect square, which is 16. So that's how we get that. And then what's left is 5. So we put that under a radical. And we end up with plus or minus 4 radical 5. And this one we can do as the square root of 4 times the square root of 7. The largest perfect square factor of 28 is 4. So we put that under here. So it simplifies. So we end up with plus or minus 2 radical 7. Okay. So the domain, so remember this point here is going to be negative 2 radical 7. This point here is 2 radical 7. The vertices on the major axes are going to be up here. We're going to have 4 radical 5. And we're just giving the x and y values, of course, right? We know these are going to be ordered pairs once we represent them, okay? And down here, that y value is going to be negative 4 radical 5. So once we have put those down, we can draw our ellipse, right? So the domain is going to be running from negative 2 radical 7 to 2 radical 7. Closed interval, of course, both endpoints included. The range is going to be the closed interval from negative 4 radical 5 to 4 radical 5. Let's see, the foci, we need to find the foci. We have the domain and range. The center is, of course, easy. That's at 0, 0. We can handle the vertices very quickly as well. The vertices are at 0. Remember, this is a vertical ellipse. 0 plus or minus 4 radical 5, right? The endpoints of the minor axes, which we have called the co-vertices, are going to be at plus or minus 2 radical 7, 0. All right. So we need to find C. The one I like to remember, which is easier for me, is b squared plus c squared equals a squared. Okay, because that one I can easily solve for other variables as I need. So here I want c, so I get c squared equals a squared minus b squared. So c squared is going to be a squared, which is 80, and b squared minus b squared, which is 28. So we get c squared equals 8 from 10 is 2, 2 from 7 is 5, so we get 52. So c values are going to be at plus or minus square root of 52. Let's break down 52 2 goes into it 26 times, 2 goes into 26 13 times, and 13 goes into 13 one time. We see one perfect square, which is 4. So we can write it as plus or minus square root of 4 times the square root of 13. So we end up with plus or minus 2 radical 13. So remember, those always lie on the major axes. So we're going to say that the foci are going to be at 0 plus or minus 2 radical 13. Remember, that's 2 points, right? One of them is 0, 2 radical 13, and the other is 0, negative 2 radical 13. All right, that's how you would do that one. So the numbers are a little bit more interesting, but not really more difficult, right? But remember, the main point here was that if you're not in standard form, first go to standard form before you do anything else. Okay? That's how you handle that one. All right, next we want to look at the generalized standard equations for translated ellipses. In other words, these are also in standard form, but they're the generalized version for ellipses that have been moved, right, from away from 0, 0 possibly. H and K could be 0, 0, but they usually will be other numbers, of course, if we're dealing with translated ellipses. Now, in this format, the center, instead of being at 0, 0, it's going to be at HK, again, which of course could be 0, 0, but usually are something else. The vertices, well, they're going to get shifted, right? So instead of them being at A0 and negative A0, they're going to be at H plus AK and H minus AK. Basically, all you have to do is, you know, instead of stressing about trying to remember that, just remember that you're going to start at the center, wherever it is, and go A units to the right and A units to the left. That's the easiest way to think about it for these horizontal ellipses, of course. And the foci are going to be at H plus CK and H minus CK, same business, just move it appropriately. The length of the major axes is still going to be 2A, just like it was before. The length of the minor axis is going to be 2B. And the distance between the center and either focus is C, which we know can be found using this formula. And here, of course, A is going to be greater than B, and both are going to be positive values here, right? Greater than 0. Now, if you have an ellipse with a vertical major axis, just like before, the only thing that changes is the location for the B squared and the A squared switch, right? And of course, the shift here is going to be vertical, right? So the vertices are going to be at HK plus A and HK minus A. The foci will be at HK plus C and HK minus C. The length of the major axis will be 2A, and the minor axis will be 2B. Again, none of these change, right? These relationships between A, B, and C remain intact. All this will become clearer when we look at some examples. But before, there is one other thing we want to discuss before we look at some examples. Now, what I do want you to note is the fact that the ellipse itself does not represent the graph of a function, right? Because notice it fails the what? The vertical line test. But whenever you do have an ellipse, you do have a pair of functions associated with it. If I only look at the top half, like this, or the bottom half, notice that both of those would pass the vertical line test. So if I could get an equation that would describe these two halves, then I would have basically two equations for two functions associated with this ellipse. And to do that is very simple. Let's say you start with this ellipse, for instance, x squared plus 9 plus y squared over 16 equals 1. All I have to do is go ahead and solve this equation for y. Remember, because we want to give y in terms of x, that's how we handle functions, right? So to do so, what I'm going to do is I'm going to multiply both sides of the equation by the common denominator, which will of course be 9 times 16. So we multiply both sides by 9 times 16. So here the 9's cancel out, we get 16x squared, plus here the 16's cancel out, 9y squared equals 9 times 16, which is 144. Remember, we're solving for y, so we move the 16x squared to the other side. We end up with 9y squared equals 144 minus 16x squared. So you get y squared equals 16 minus 16 over 9x squared. And finally, you apply the square root property and get y equals plus or minus square root of 16 minus 16 over 9x squared. Now, the positive case will graph this part, and the negative case will give you the graph of that part. You can easily try that by graphing it using a graphing calculator like Desmos and verify that. All right, so here notice I've typed them in to save us some time. If I look at the positive case, that will give me the red graph on the top. Let me remove that one, okay? And if I look at the negative case, that will generate this one. If I look at each one alone, notice they both represent functions, whether I look at the blue one or the red one. So with every ellipse, there is associated two different functions that you can obtain. Okay, next we want to go ahead and graph this translated ellipse. We do notice that it's going to be a vertical ellipse because the expression, the number under the y term is the larger one, so that's going to be our a squared. So a squared equals 9, and our b squared is going to be 4. So that means a equals plus or minus 3. And this implies that b is going to be plus or minus 2. So now we know that because of that plus 3, the center of this ellipse is not going to be at 0, 0, but it's going to be rather at -3. Remember, when it's +3, it's actually a movement of 3 units to the left because it's x minus h. So how can you write x plus 3 in the form of x minus a number? It would be minus -3, right? So we use -3, and here it's already a negative, so that's just going to be 5. So the center is going to be, the k value is going to be 5. So we can see here's the new center. What you can do is you can draw yourself a pair of axes right there. That's going to make graphing the ellipse really simple at that point. So now once you have your center at -3, 5, then to get these points, this is why I was telling you, don't stress about memorizing all that x plus a, h, and all that, because all you got to do is look. You want to get these 4 points, right? And those are easy to get because you know that this piece here, these two pieces that make up the major axes are going to be 3 units each, right? Lengthwise. And you know that these two pieces are going to be the b parts, so it's going to be 2 each. All right, so to get, for example, that point, that top vertex, right? You're going to need to realize that it's going to have the same x value, right? So the x value isn't going to change. But to get the y value, you're just going to take 5 and add 3 to it, right? Easy. For this the vertex down here, which we've been calling v prime, you're going to realize it's the same x value. For the y value, you're just going to take the 5 and subtract 3 from it this time. So you get what? 3, 2. See how easy that is? Now, for the covertices, which we've been referring to as v bar, right? And v prime bar. I mean, v bar prime, I should say. You realize that it's going to be at the same y value. So this time, the y value doesn't change. For the x value, we take the -3 here and add 2 to it for this one. So we get -3 plus 2. So it's going to be -1. And for this one, we're going to be at the same y value. But for the x value, we're going to go -3 minus 2, right? So we get -5. And of course, notice that makes sense in our graph as well. So that's how we can easily find all that. So we just basically did a bunch of it, right? We found the center. This is the center. We found the vertices, right? They're -1, 5 and -5, 5. We found, sorry, those are the covertices. We found the vertices at -3, 8 and -3, 2. The covertices, which are the endpoints of the minor axes, are -1, 5 and -5, 5. Now, the only thing left is the foci and the domain and range. Domain and range are easy. Let's go ahead and write those down. Domain is going to be from this x value, which is -5, to this x value, which is what? -1. So closed interval from -5 to -1. Make sure to use brackets. The range is going to go from this y value, which is 2, to this y value, which is 8. Right? And now we just have to find the value of c. So we know that, remember, this capital C is different from the C we're talking about. Capital C stands for center. We're looking for lowercase c, which is the, in this case, the y coordinate of the foci, right? So we know that b squared plus c squared equals a squared. So c squared equals a squared minus b squared. So c squared equals a squared, which is 9, minus b squared, which is 4. So we get c squared equals 5. So c is going to be plus or minus radical 5. So the foci, which are going to be on the vertical axis here, are going to be, to get this one here, right? We're going to realize it's going to be at the same x value as that. Its y value is going to be radical 5 more than 5. So 5 plus radical 5. For the one down here, again, we know it's going to be at the same x value as the center. And the y value this time is going to be 5 minus radical 5. Because remember, this piece and this piece we have found are both have length radical 5, right? So they will be at -3 and then 5. This one was 5 minus radical 5. So 5 plus or minus radical 5. If you want to write them separately, you would just say f at -3, 5 plus radical 5, and f prime at -3, 5 minus radical 5. All right, so that's basically how you handle this one, okay? All right, so make sure that you can comfortably handle that, and we'll proceed. All right, next we're going to find the equation of an ellipse with x-intercepts at plus or minus 8, 0, and y-intercepts at 0, plus or minus 4. Firstly, I want you to notice that if you have an ellipse which is centered at 0, 0, and let's say, for example, with a horizontal major axis, then you know that the standard form is the following, right? Now notice that it's very easy to find the intercepts, because let's say I want to find the x-intercepts. That means I'm going to put the y value equal to 0, right? Remember, at the intercepts, the y value is 0, right? So I would end up with, if y is 0, I get x squared over a squared equals 1, because this part becomes 0, right? This fraction. So I get x squared equals a squared. So that means x equals plus or minus a, applying the square root property. Notice that the y-intercepts are easy to find as well, because at the y-intercepts, the x value is 0, right? At both of these y-intercepts. So if I let x be 0, right, that implies this fraction becomes 0. So I just get y squared over b squared equals 1, which implies y squared equals b squared, which of course implies y equals plus or minus b. So plus or for a horizontal ellipse, the vertices are at plus or minus a0, and the covertices are at 0 plus or minus b, and those happen to also be the what? Be the intercepts of the ellipse. So we pick the larger ones to represent a, right? So we know that we're going to have an ellipse looking exactly like this, right? So this indicates that our a is 8 and our b is 4, right? So we get x squared over a squared plus y squared over b squared equals 1. So x squared over 8 squared, which is 64, plus y squared over 4 squared, which is 16, equals 1. And there we have the equation of our ellipse. So very simple once you understand that the intercepts for an ellipse centered at 0, 0 are none other than their what? The vertices as well as the covertices. Next, we want to find an equation of the ellipse with foci at plus or minus 3, 0, and 10 for the length of the major axis. Now, we know that the length of the major axis is 2a, right? So that means 2a equals 10, which is going to tell us a equals 5. Now, of course, to write the equation, we'll also need b, and we don't have it, but we have a, and since these are the coordinates of the foci, we know that c should be 3. So therefore, using the fact that b squared plus c squared equals a squared, we can easily find the value of b. So we solve this for b, so we get b squared equals a squared minus c squared. So b squared is going to be 5 squared minus 3 squared, so b squared equals 25 minus 9, so b squared equals 16. So b is going to be plus or minus 4. But as far as plugging into our equation, since we square, the plus or minus don't matter. We know that we're actually only interested in b squared. We just wanted to find b so that we could graph it if we wanted to. Here we don't need to, but it's good to be able to. So we get x squared over a squared, which is 25. If a is 5, of course, a squared is going to be 25. Plus y squared over b squared, which is 16, equals 1. And that's all we have to do, okay? All right, next we want to go ahead and find an equation of the ellipse with center at 3, 2, as indicated here. A vertical minor axis of length 16. So here's the vertical minor axis of length 16, and c equals 6. Now, because of the fact that the minor axis from here to here is 16, that's going to make each of these two pieces 8, right? And that's going to be b. So in other words, 2b is equal to 16, therefore b equals 8. Your best bet when doing these translated ones is go ahead and draw yourself a new pair of axes at the new center, and everything else will follow very easily from that. So notice that the new center is at 3, 2. So now we can find pretty much anything we need, right? We know that c is equal to 6. Let's go ahead and find a real quickly. We have b and we have c, so it should be easy to find a, right? Because we know that b squared plus c squared equals a squared. Remember, you can pick the one you like to memorize. This is the one that's very easy for me, so I just use this one. So we have 8 squared plus 6 squared equals a squared, so 64 plus 36 equals a squared, so that's 100 equals a squared. So a is going to be plus or minus 10, but since I'm interested in the length of the a piece, I'm only going to be needing the positive 10, right? So that means we have pretty much everything that we would want to write the equation, right? We know the center, and now we've used the c to find a, so we're ready. So remember, this is going to be a horizontal ellipse, so it's going to be of the form x minus h squared over a squared plus y minus k squared over b squared equals 1. We associate a, as you recall, with the major axes, okay? So we're going to have x minus 3 squared over a squared, which is 100, plus quantity y minus 2 squared over b squared, which is going to be 8 squared, which is 64, equals 1. So there's the equation of the ellipse as described in this problem. So go ahead and make sure that you understand that, and we'll proceed. Okay, here's one that's a little bit different. We're going to find an equation of the ellipse with foci at 0 plus or minus 5 and containing the point 24, 5. All right, that should have been a comma, which we fixed through the magic of Microsoft Word. All right, so all we're given is basically c, right? We know that c is 5. and we're given 1 point on the ellipse. Now, we do know a little bit more. We know that since the foci are on the y-axis, this is going to be a vertical ellipse. So in other words, we know that A is going to be a y value, right? So let's see what we can get out of this. So we know the equation is going to have the form x squared over b squared plus y squared over a squared equals 1. Now we do know that b squared plus c squared equals a squared, right? So we know c is 5, so b squared plus 25 equals a squared. So if I solve for b squared, I get b squared equals a squared minus 25. So I can replace the b squared with a squared minus 25 plus y squared over a squared equals 1. Now, at this point, it's hopeless, right? We got 4 letters we need to deal with, or 3 letters, right? But remember, the point 24, 5 is on this ellipse, so it has to satisfy the equation. So we're going to substitute 24 for x and 5 for y. So 24 squared, let's go ahead and figure that out. 24 squared, 576. So we get 576 over a squared minus 25 plus y squared, which is going to be, as you can see, 5 squared like so. Okay, so now we're going to go ahead and try to solve it, because now we finally have one equation in one unknown, right? So we know that the LCD is going to be a squared times a squared minus 25. So we'll go ahead and multiply both sides by the LCD. Don't forget, that means every term has to get multiplied by a squared times a squared minus 25. The first term on the left side, the second term on the left side, and of course the right side. We multiplied both sides by the LCD. So now we notice that we have some cancellation possible. Here we can cancel the a squared minus 25s. Here we can cancel the a squares. And that should do it as far as cancellations. So we get 576 a squared plus 25 times a squared minus 25 equals, I'm going to go ahead and multiply the right side out. So I get a to the 4 minus 25 a squared. All right, so let's go ahead and multiply this 25 into this group here. So we get 576 a squared plus 25 a squared minus 25 times 25, which is 625, equals a to the 4 minus 25 a squared. Now we're going to go ahead and move, let's go ahead and combine these first, and then we'll move everything to the right side. Always simplify each side completely before you move things around. So 576 plus 25, 601. So we have 601 a squared. Let's see if we can keep this going up like that. Okay. minus 625 equals a to the 4 minus 25 a squared. Now we'll move everything to the right side and get a 0 on the left side. So we get 0 equals a to the 4 minus 601 a squared minus 25 a squared, and then plus 625. So we get 0 is equal to a to the 4 minus 626 a squared plus 625. Okay, those numbers look a little scary, but they're not that bad if you look at it, because now we're going to factor that. So I'm just going to factor it by trial and error. I know I need a squared and a squared. Now, two numbers whose product is positive 625 and whose sum is negative 626. So that's just going to be negative 625 and negative 1, right? So we get 0 is equal to a squared minus 625, or 0 is equal to a squared minus 1. So this one gives me 625 is a squared, or this one gives me 1 is equal to a squared. Now I don't really need to find a, because I'm going to need a squared to find b anyway, right? And for my equation, I'm going to need a squared and b squared. So I'm just going to go here and try to find b squared. Now, if a squared is 625, b squared, so if a squared is 625, that implies b squared is going to be a squared minus 25, so 625 minus 25, which is 600. And if a squared equals 1, that implies b squared is going to be 1 minus 25. Now this is actually less than 0, so we don't want that one because we don't want the square to be negative, and so therefore that's our only option. So now we're ready to write our equation. We get x squared over b squared, which is 600, plus y squared over a squared, which is right here, 625, equals 1. All right, so that one was more interesting, right? A little bit of algebra involved. Go ahead and make sure that you can handle that on your own, and we'll go ahead and proceed. Before we do, however, I want you to notice how when a and b are close, and therefore a squared and b squared are close, the ellipse becomes very much circular. We already said that if a and b are exactly equal, then we actually get a full circle, perfect circle, right? But when a and b are really close, we also get really close to what? To circular. All right, next we want to go ahead and graph this equation. Now, if you recall, a little while back, we talked about functions associated with ellipses having this form. So the best way to figure out how to graph something like this is to actually go backward and turn it into an ellipse. And then here we have the positive case, so you're just going to graph the top part of the ellipse. So if we square both sides, we get y squared over 16 is equal to 1 minus x squared over 9. Move the negative x squared over 9 to the other side, so we get x squared over 9 plus y squared over 16 is equal to 1. So we know how to graph the ellipse, right? It's easy. And all we have to do is just not graph the bottom. But we know that because this is larger, that's going to be a squared And because this is the smaller, that's going to be b squared, like so. So we're going to have vertices at 0, 4 and 0, -4, and co-vertices at 3, 0 and -3, 0. And we know that we can then graph the full ellipse, but we're going to make sure that we only graph the top part. Now, what is the domain and range of this function? And yes, it is a function. The domain obviously runs from -3 to 3, so closed interval from -3 to 3, and the range runs from 0 to 4. All right, so that's how you would graph something like that. All right, so here we have another equation that's given to us in a form closer to the general form than to standard form. So we're going to go ahead and try to put in a standard form, then it'll become real easy to graph. So we go ahead and put the x terms next to each other and leave some space, put the y terms next to each other. And leave some space again because we're going to be completing this square. Now, notice that if I go ahead and take out a 9 from those two, I'm left with x squared plus 4x, right? I need to take 1/2 of 4, which is 2, and then square it to complete the square, right? So keep track of that. For the next piece, we're going to take out a 49. That leaves us y squared minus 10y. So to complete the square, I need to take 1/2 of -10, which is -5, and I need to square that to get 25. So we're going to add 25. Now, here's where you have to be extremely careful. We're not just adding a 4 to the left side so that I can just add a 4 over here. We're actually adding 9 times 4, right? That's 36. So I need to add 36 to balance that off. And over here, I'm not just adding 25. I'm adding 49 times 25 to this side, right? So we need to figure out what 49 times 25 is. That's 1225. So to keep the balance, I need to add 1225 as well. Okay? So now we have 9 times quantity x plus 2 squared plus 49 times quantity y minus 5 squared equals. Now we need to figure out what all that is. All right, so -820 plus 36 plus 1225. And that gives me 441. All right, so obviously you know that with the standard forms, we always want to have a 1 on the right side, right? So we go ahead and divide both sides of this equation by 441, which of course the left side splits. That means each of these two terms is going to get divided by 441. And now we need to see if 9 goes into 441. It better, otherwise we're going to have issues. So 441 divided by 9. Now, do I already know that 9 is going to go into it? Do we? Remember, the divisibility rule for 9 is very simple. It's just like 3. You add the digits. If the sum is divisible by 9, so is the number. What's 4 plus 4 plus 1? That's 9. I already know it's going to go into it, so I'm going to confidently divide, and I get 49. So I get quantity x plus 2 squared over 49 plus, so of course that means 441 over 49 should be 9, as of course it is. So then we get quantity y minus 5 squared over 9 is equal to 1. All right, now we're ready to go ahead and graph it. Notice the center is going to be shifted. It's going to be at -2, 5. I'm going to go ahead and create an axis right there. Once you draw your new axis where the translated center is, everything becomes really easy. So we know that now this center is -2, 5. So because the 49 is under the x term, we know that this is going to be a horizontal ellipse with a squared equals 49. So therefore a, here I'm only interested in the length of the a piece, so I'm just going to use the 7. And we know that b squared is 9, so therefore b is going to be 3. All right, so to get the vertices, right, we start at the center and move 7 to the right and 7 to the left. So one vertex is going to be at -2 plus 7, which is 5, and the same elevation, 5, right? The other vertex, the left one, is going to be at -2 minus 7, so it'll be what? -9, and then the same elevation. As far as the minor vertices or the co-vertices, right, we're going to have the same x. They're both going to have the same x value, right? For the y value, I'm going to start with the 5, and I'm going to add 3 for the top one to get 8. And I'm going to subtract 3 for the bottom one to get 2. So those are the vertices and the co-vertices. And we have the center, and that's it. We're done. There's our equation. These are the vertices. These are the co-vertices, also called the endpoints of the minor axes. And that's it, basically. And that's standard form. Next, we're going to take a look at a couple of applications of ellipses. In this problem, we're looking at a one-way road that passes under an overpass in the shape of half an ellipse, as depicted here. It's 25 feet high at its center and 20 feet wide. So that means this piece from here to here and the piece from here to here each are 10 feet. And we want to see if we have a 16-foot wide truck, so depicted here, what is the tallest such truck that can pass under the overpass? Now, this can be handled very easily if we position this overpass properly so that the center here is also the center of the Cartesian coordinate plane. So this point becomes 0, 0, and this becomes the y-axis. So this y value here is 25, and basically what we're looking for is the y value here, which is the height of the truck, when the x value is 8, because if the entire truck is 16 feet. That means from here to here should be 8, right? So we need an equation for this half ellipse, which is of course a function, but if you recall from a previous problem, it's a lot easier if we go ahead and quickly find the equation of the ellipse itself first. And of course, we know that for this ellipse, which is a vertical ellipse, given that the major axis is the longer one here, the vertical one. So we know that this point here is going to be B, and it's at 10, and it's -10. So this is our B here, and our A is going to be the 25. So we can write the equation of the ellipse pretty quickly. Because it's a vertical ellipse, we know it's going to have the standard form x squared over b squared plus y squared over a squared equals 1. So we get x squared over b is 10, so 10 squared plus y squared over a squared, which is going to be 25 squared, equals 1. So we go ahead and simplify that. We get x squared over 100 plus y squared over 625 equals 1. Now we go ahead and solve this for y so that we can get the equation of this function depicted here. So we get y squared over 625 equals 1 minus x squared over 100. So multiplying both sides by 625, we get y squared is equal to 625 minus 625 x squared over 100. We'll go ahead and reduce this to make the numbers a little bit nicer. It looks like at least 25 goes into both of them, so we know that 625 divided by 25 is 25, and 100 divided by 25 is 4. So if we cross cancel, we get 25 up here and 4 down here. So basically we have y squared equals 625 minus 25 x squared over 4. So y is going to be plus or minus the square root of that, but we're interested in the top half of this ellipse, so we're going to only take the positive case. So we're interested in positive square root of 625 minus 25 x squared over 4. All right, so the y value of interest is this y value corresponding to x equals 8. So all we have to do is now substitute 8 for x and find the corresponding y value. So we get y equals square root of 625 minus 25 times 8 squared over 4. And now it's just a matter of computing that. So we have square root of 625 minus 25 times 64 divided by 4. And we get 15. So basically, the tallest truck that can pass under should be just slightly under 15 feet, of course, because at 15 feet it will scrape the top of the truck. So we'll want to be just slightly under 15 feet. All right, so that's how you would handle an application like that. So please make sure that you understand that and you can handle that on your own, and then we'll move on. All right, in this next problem, we're looking at a lithotripter, which is a machine used to crush kidney stones using shock waves. The patient is placed in an elliptical tub with the kidney stone at one focus and the source of the beam that's going to be crushing the stone at the other focus. And then a beam is projected from the beam source to basically hit the ellipse and then reflect back to crush the kidney stone. And the equation of this particular one is given here: x squared over 64 plus y squared over 36 equals 1. We want to know we want to find the distance from the ellipse's center to the kidney stone, as well as to the beam source. Of course, as you know, those two distances are the same, and this is actually a very, very simple problem. It's a perfect example of something that sounds real scary and complicated, but it's really, really simple. So I want you to actually pause and see if you can handle this on your own, and then come back and see if we basically did the same thing. All right, I think you've realized that all we have to do here is, again, strategically place the center of the Cartesian coordinate plane right there. And then all we have to do is find C. Remember this length here, from the distance from the center of the ellipse to the focus, to either focus, is that length C, right? So we know that this is a horizontal ellipse, right? So the A is going to be 8, and B is going to be 6, which is of course the square root of 36. So we have A equals 8, B equals 6, and we're trying to find C, and we know that B squared plus C squared equals A squared, or at least that's the one that I like to memorize. It's the simplest one for me. You may have your own favorite version of this to memorize. And since we're solving for C, I'm just going to go ahead and solve this for C. So we get C squared equals A squared minus B squared. So we get C is going to be we're interested in the positive version. So the positive square root of A squared minus B squared. So we get the square root of 64 minus 36. All right, we didn't quite even have to find A and B, but it never hurts. All right, so we get the square root of 6 from 14 is 8, and 3 from 5 is 2, so 28. If we want, we can actually write that as the square root of 4 times the square root of 7, because 4 is the largest perfect square factor of 28. So we end up with 2 radical 7. So basically, the answer to both of those questions is going to be the same, and it's going to be 2 radical 7. The units, of course, will be whatever units are being used, most likely feet here, right? So we just use the units that are provided. All right, and that's how you would handle that one. A much easier problem, actually. So there you are. The last topic we're going to look at today is that of the eccentricity of a conic section. One of the ways we can define a conic section is using this quantity called the eccentricity. A conic is the set of all points in a plane whose distances to a fixed point called the focus and a fixed line called the directrix are in a fixed ratio called the eccentricity, and we use the letter E, lowercase e, of the conic. Now, as it turns out, a parabola will have eccentricity exactly 1. The eccentricity of a circle is 0. For an ellipse, it's some quantity between 0 and 1. And for a hyperbola, it's some value greater than 1. This will all make sense in a minute when we get into a little bit more detail. But I just wanted to show you that one of the ways that you can have a universal definition for all conics is using this quantity called eccentricity. Basically, the eccentricity of a conic section is a non-negative real number that uniquely characterizes its shape. Think of eccentricity as a measure of how much a conic section deviates from being circular. The definition that we use for eccentricity is basically C over A. E equals C over A. Well, E is the eccentricity. C is the distance from the center of the conic section to one of its foci. And A is the distance from the center of the conic section to one of its vertices. Of course, as you know, a parabola doesn't have a center. So in this case, what we do, we call A the distance to its directrix, which by definition is going to be the same as the distance to its focus, if you recall from our lecture in the last video about parabolas. Notice that both the ellipse and the hyperbola, because they have 2 focuses, they're also going to have 2 directrixes. Okay, so here is one of them shown here. The other one will of course be on the other side, and the same goes with the hyperbola. We're showing one directrix here, and we'll have another one on this side. And the point is that for all of these conics, the ratio of the distance here to the distance here is going to be proportional for all the points. So in other words, the ratio of this segment here to that segment is going to be the same as the ratio of this segment to that segment, etc. So now for a parabola in particular, we know that the distance from the focus to any point on the parabola is going to be exactly the same as the distance from the point to the directrix. So since it's that ratio which gives the eccentricity, you know that the parabola is going to always have eccentricity equal to 1. The directrix of the conic section is the line which, together with the point known as the focus, serves to define a conic section as the locus of points whose distance from the focus is proportional to the perpendicular distance from the directrix, with r being the constant of proportionality. If the ratio r equals 1, the conic, as we said, is a parabola. If it's less than 1, notice with these, that length is always going to be less than that length. So when you divide the smaller length by the larger length, you're going to end up with a ratio which is less than 1, then you get an ellipse. For a circle, r turns out to be 0, and notice that with these, the situation is different. That distance from the focus to the point on the hyperbola is going to be larger than the distance to the perpendicular distance to the directrix. So that ratio is going to be greater than 1, and that's how you know you have a hyperbola. Now, as we mentioned, hyperbolas and non-circular ellipses are going to have 2 distinct foci and therefore 2 associated directrices, each directrix being perpendicular to the line joining the 2 focuses or 2 foci of the figure. Okay, we can actually calculate the eccentricity for each of these conics based on what we just discussed. Remember that for the parabola, since we don't have a center, so to speak, we actually use this formula, which is the distance between any point on the parabola to the focus divided by the perpendicular distance from the same point to the directrix. And as we know, by definition, those two distances are the same, if you recall from our parabola lecture. So the eccentricity for all parabolas is always going to be 1. Now, for the ellipse, circle, and hyperbola, we can use the C over A formula that we discussed, E equals C over A. Now, remember that for an ellipse, C is the square root of A squared minus B squared. We've been working with that all day, over A. Now, we know that C is always going to fall somewhere between 0 and A, right? 0 being here, A being here. So as far as the length of C is, of course, concerned, we're talking about, because this may not even be centered at 0, 0, but still that length is going to be A, and that length is going to be C according to our terminology for ellipses, right? So if we divide all three sides of this three-part inequality by A, we end up with 0 divided by A, which is 0, less than C over A, less than A over A, which is 1. So this is for why for an ellipse, the eccentricity is always going to be somewhere between 0 and 1. For a circle, remember that this is the center radius form of the equation of a circle, and if we divide both sides by r squared, we end up with this equation. And we know that for a circle, which is a special kind of ellipse, A and B are the same, so we end up with C being the square root of A squared minus B squared, becoming the square root of R squared minus R squared, which is 0. So the eccentricity for a circle is always going to be C over A, which is 0 over A, and therefore 0. And so in other words, how far away is a circle from being circular? None. Okay, that's basically how you interpret that. And of course, the closest to a circle would be a non-circular ellipse, whose eccentricity is going to be somewhere between 0 and 1. And from there, we move on to shapes that become quite distant from being circular. First the parabola, and then really distant from being circular is the hyperbola. Here the eccentricity is C over A. In our next video, you'll learn that C is actually going to be the square root of A squared plus B squared rather than the A squared minus B squared for an ellipse, and over A. Now, we know that the square root of A squared plus B squared is going to be greater than A, because remember, just the square root of A squared itself is just going to be A. So now you're adding to that some positive quantity to that. So of course this square root is going to be larger than A. So therefore C over A, right, is going to be some number which is larger than A divided by A. And that's always going to be a result which is greater than 1. Therefore, for all hyperbolas, the eccentricity is going to be greater than 1. Here are a few figures to give us a feel for eccentricity. And we notice that the eccentricity here is rather low, because if you look at this, it's a rather circular kind of ellipse. As you get further and further away from being circular, the eccentricity is going to get larger until it gets close to 1 for a really, really narrow ellipse like that. Here we have a really wonderful animation depicting eccentricity by Mr. Quinn using the wonderful app called GeoGebra. And notice that we start with a circle which has eccentricity 0, and the center and the both foci have collapsed into one point, and as we start increasing the eccentricity slowly, notice as soon as we go above 0, we start getting an ellipse, and but it's still quite circular. As we increase the eccentricity, notice it becomes less and less circular, and the more elongated it gets and the more it loses its circularity, we get further and further away from 0 and move closer to 1. Now this will be an ellipse. We'll continue to have an ellipse all the way until we hit 1. So even though we're going to go outside the visible frame here, we know that until this hits 1, it's still going to be an ellipse. Now there's only one instant at exactly 1 where we get a parabola, and as soon as we go above, it's hard to get it like that, so we can just type it in. That's the nice thing here. So right there we have the parabola, and as soon as we start moving away toward higher values after 1, we start getting the hyperbola. See? And there we are. See? Very, very nicely done. All right, so there's a nice animation showing us the concept of eccentricity of a conic section. Next, we're going to go ahead and actually calculate the eccentricity for a couple of ellipses, and that should do it for the day. Now here, notice we have a relatively elongated vertical ellipse, so we expect the eccentricity for this ellipse to be pretty close to 1. So let's go ahead and calculate and see what it turns out to be. So we know the formula is E equals C over A. Now we can calculate C because we know that B squared plus C squared equals A squared. So C squared equals A squared minus B squared, and of course we know that the larger one is going to be A squared, so A squared equals 36 and B squared equals 11. So C, and I'm interested in the length, so I'm just going with the positive version, so it's going to be the square root of A squared, which is 36, minus B squared, which is 11. So we get C equals the square root of 25, which is 5. So for the eccentricity, we get E equals 5 over, and remember, since A squared is 36, A is going to be 6. All right, so just as we expected, the eccentricity of this ellipse was quite high for an ellipse, and it was close to 1, 5/6. All right, let's do one more and we'll call it the day. All right, for this example, we're going to revisit an ellipse which we already saw in example number 7. And if you recall from that example and also from this graph, you can see that this is a nearly circular ellipse. So we would expect the eccentricity to be much closer to 0 than it would be to 1. So let's go ahead and verify that. As we know, we can find the eccentricity using the formula E equals C over A. And from the equation here, we can see that this larger denominator will correspond to A squared. So A squared equals 625. B squared will be 600. And we know that for an ellipse, b squared plus c squared equals a squared, right? Since we're interested in finding c, we're going to solve this equation for c squared. So we get c squared equals a squared minus b squared. So we get c squared equals 625 minus 600. So c squared equals 25. So c will be the positive square root of 25, or 5. Now we also need a. Since we have a squared here, we can quickly get that. A will be the positive square root of 625, which is 25. So now we're ready to find e. So we're going to get e is equal to c, which is 5, over a, which is 25. And we end up with e equals 1/5, which is the same as 0.2. And as we can see, that eccentricity is closer to 0 than it is to 1. Whereas if you remember the last example, which was more of an elongated ellipse, the eccentricity ended up being closer to 1. Let's take a quick look at that. See, for this more elongated ellipse, we got the eccentricity of 5/6, which is of course closer to 1 than it is to 0. All right, so that should pretty much cover it for today, and you take care until our next video.